In this video, I want to take a look at a method of using determinants to solve systems of equations. This is called Cramers Rule. Cramers Rule is stated as follows. If you've got ax equals b as a square system, so n equations and n variables, and you know that the determinant of the coefficient matrix is not equal to 0, then the system has a unique solution. Moreover, the solution is given by x1 is the determinant of a1 over determinant of a, x2 is the determinant of a2 over determinant of a, and so on, where those ai's, a1, a2, up to an, are obtained by replacing the ith column of a with the entries in b, where b is the coefficients here, is the constant coefficients over on the right-hand side of that system. Okay. Here's the proof. Since the determinant is not equal to 0, we know that a is invertible. So we can solve the system simply by multiplying both sides of the equation by a inverse on the left. Right? And we get that x is a inverse of b, or a inverse times b. Now, in the previous video, we saw that a inverse is the adjoint of a divided by the determinant of a, or 1 over the determinant times the adjoint. So I replace the inverse with that. And now I can just say what the adjoint is. It is the transpose of the matrix of cofactors, right? So this first column are all the cofactors of a from the first row of a. And the second column is all the cofactors of a from the second row of a, and so on. And now I can actually do that multiplication, that this matrix times that matrix, n by n, n by 1, the result is n by 1, so this is just a column matrix here, times the constant 1 over determinant of a is going to equal the n by 1 matrix on this side. So each of the xi's now, x1 is going to be this thing divided by det a, x2 is going to be this second thing divided by xa, all the way down to xn being the last thing, the nth entry there divided by determinant of a. So if I grab the ith one here, xi is this. Okay. Now what I want to point out is that that numerator looks an awful lot like a determinant. It's a number times a cofactor plus another number times a cofactor and so on. And in fact, it is a determinant of this matrix. It's this determinant right here. So what I've tried to illustrate here is that I've taken the matrix A, these are all the entries of A, but the ith column is replaced by the B's that are on the right-hand side of the system, right? All those constants on the right-hand side of the system. So this is first row, first column, first row, second column, third column, first row, I minus first column. This would be the ith column, but it has the first entry of B in it. And then we got the I plus first column all the way up to the last one. Right? So this is the ith column, and it's got all those B's in it. Now, if I take the determinant of that, cofactor expansion down the ith column, I would have B1 times the cofactor corresponding to that spot. Well, that's the first row ith column, so it's B1 times cofactor 1i. Then plus B2 times the cofactor for here, well, that would be cofactor 2i, right? And that's that, and so on. And notice that this matrix that I'm taking the determinant of is not matrix A. All the cofactors that are being referenced here are exactly the same as the cofactors from A because they don't use the ith column. Every one of them is one of the cofactors from the ith column, so they're using the entries in all the other columns. Okay. So there it is, that xi is this determinant divided by the determinant of A, which is what the statement said it would be. Right. All right, let's do an example here to see this in action. So here's a 3 by 3 system. X plus y plus z equals 2, 2x plus y minus z equals minus 3, and x plus 3y minus 2z equals negative 11. The coefficient matrix is A. It's 1, 1, 1, 2, 1, minus 1, 1, 3, minus 2. That's just grabbing the coefficients in front of the variables on this side. And I can look at the determinant of that, and I find that it's equal to 9. Okay, so that's not equal to 0, so I know that A is invertible, and I know that there is a unique solution, and according to Cramer's rule, I get it this way. Sorry. So x is the first variable. The denominator in each of them was the determinant of A. I don't have to calculate that each time. I know it's 9. But the numerator is, take a look at matrix A here and replace the first column by the numbers here, 2, minus 3, minus 11. That's what I have right here. The second column matches with A, the third column matches with A, but the first column matches with those numbers. Take the determinant of this, it turns out to be 9, and 9 divided by 9 is 1. My claim is that the solution to this equation will have x equals 1. Likewise, to calculate y, being the second variable, I'm going to take A and replace the second column with the 2, negative 3, negative 11. So there I see the 2, negative 3, negative 11. The first column matches A, the third column matches A, and take the determinant of that now. That turns out to be negative 18, and negative 18 divided by 9 is negative 2. So my claim is the solution here will have y equals negative 2. And lastly, to calculate z, I am placing the 2, negative 3, negative 11 in the third column, but the first two columns match what A has. And then I take this determinant, divided by the determinant of A, 27 divided by 9 is 3. And so my claim is the solution to this differential equation, this system of equations, is x equals 1, y equals negative 2, z equals 3. And you can double check in each one, plug in the x, y, and z, and see that it makes every one of those equations true. So this is the unique solution to this system. Okay. Now, there is a reasonable question of why would we even want to do this? Taking determinants is, well, it's not that it's hard, it's just it's a lot of work, particularly as you get more variables and equations. When 3 by 3 wasn't bad, but if you had to do a 10 by 10, so you got 10 variables that you have to do essentially 11 determinants for, because the denominators are all the same, plus 10 different numerators. I mean, that's a lot of taking determinants. That's a lot of work. It just doesn't seem like a reasonable thing to do. And you're right, it isn't a reasonable thing to do. It's much less work to do an augmented matrix and do row reduction to get to reduced row echelon form to find these solutions. However, there are instances where you might be solving a system in some application where you don't really care about what all the values are. You just need to know what one of the variables is going to equal. Right? For whatever reason, it's the one you're interested in. And so you don't have to calculate everything. You can calculate just that one and not worry about the rest of them by just grabbing the appropriate one that you need. Right? On a more theoretical level, it's also convenient to be able to have an actual expression to work with if you're going to be using this to do any other algebra, any further calculations, rather than just saying, hey, yeah, you're going to do an augmented matrix, and x1 is going to be the first thing that you get when you get in a reduced row echelon form. Look at that last column. You don't really have a formula for it. You have a method of getting it, but what's the formula? What is it actually going to be? And this is what it's actually going to be. And so you just have an actual formula to then do further calculations with, which is a very definite thing to be able to do, right? Now I want to just end this this video and this chapter with a brief review of the things that we know are equivalent at this point, right? This theorem is shows up again and again in this course as we keep doing different things, and we find that even though it looks like we're doing something different, it is related to something we've been doing before, and we can say something else about a matrix being invertible, right? And so the following statements are equivalent. If A is an n by n matrix, then the definition A is invertible. That's one statement. A is invertible if there exists a matrix B such that AB equals BA equals I, right? That's what it means to be invertible. That's equivalent to the system AX, the homogeneous system AX equals 0, has only the trivial solution. That's equivalent to say that the A reduces to the reduced row echelon form of A is the identity matrix. It's equivalent to saying that A can be expressed as a product of elementary matrices. It's equivalent to the statement that the system AX equals B is consistent for every n by 1 matrix B. And it's consistent to say sorry, it's equivalent to saying AX equals B has exactly one solution for every n by 1 matrix B, and is equivalent to saying that the determinant of A is not equal to 0. Okay. Interesting thing about um, a theorem like this, which is giving you a bunch of equivalent statements. The first one is essentially A is invertible. There's a definition of what it means to be invertible. And because all of these other statements are equivalent to that, we could have used a different definition. We could have said that the definition of A invertible is that determinant of A is not equal to 0. And then it would be a theorem later that would say that if A is invertible, meaning the term is not 0, then there exists some matrix B such that AB equals BA equals the identity. That would have been a theorem rather than that being the definition, right? Because all of these things are equivalent. Any one implies the other. So if you have one, you've got them all. And if you don't have one, you don't have any of them, right? So there's a lot of things that are related to the invertibility of a square matrix, and we will continue to see more and more of them as this course goes on.